Okay, so now we have Professor Joe Eiswick from NTNU, and he will be speaking about informative spatial sampling with autonomous underwater vehicles.
Thank you so much. So I'm a statistician. So my background is in spatial and computational statistics, but I'm working mostly on earth science applications. So I'm an applied statistician. And lately I've been working a lot on design, so spatial sampling and temporal sampling, and some value information analysis in this context. So this is what I will talk about here, and I will start off with an example motivating sampling and information gathering, and then get into some AUV applications where we try to sort of guide the AUV to informative places. Let's first imagine this pirate. So this pirate is in Croatia, and he's sitting drinking in a pub, and then he's listening to someone at the neighboring table, some archaeologists at a conference, talking about a wreck that went down on an island here, maybe many years ago. And there is apparently a lot of value, or there was a lot of value on this ship. So based on this discussion, this pirate figured out, okay, so he can actually go there and dig for this treasure, or he can just ignore this. So he has two alternatives. And he also knows that he can have success or failure, so the treasure is either there or not there. And based on what he heard from the neighboring table, oops. Yeah, yeah, someone unplugged this. All right. So there's a 1% probability that this treasure is on this island. It could be on another island, but he knows that the value is 100,000 euros, so it's pretty good if he finds it. But then if he goes there and dig for the treasure and there is nothing there, then he would lose 10,000. So this is a decision situation that he has. So then you can draw a tree out of this. So at the first stage here, at that square, the pirate decides whether he should dig or not dig. And if he goes there to dig, there's uncertainty, so he makes this decision under uncertainty. And if there's a treasure, he gets 100,000, but that happens only with 0.01 probability. And in the other case, you lose 10,000. So then, based on expected values here, it's better for him not to dig, actually. So he should stay away. Then he has an option here, and this is to get information. So now he knows a clairvoyant in the neighborhood, so he can go and ask her, or he can get a detector, like a metal detector, that will find some of these coins. So these are potential information gathering methods that can help him make a better decision. And then this is a concept from operations research, decision analysis, called value information, where you actually compute upfront, based on expected values, how much this data is worth. And you do this in a prior setting and in a posterior setting, and then you see how much you gain. What's the information gain? So if we go to this clairvoyant case, you can then first here have a circle where the uncertainty is revealed. So this clairvoyant tells him there is a treasure there, but she only does so with this right probability of 0.01. And if you get to know that there's a treasure there, it's easy to make a decision. So then you should dig. In the other case, where she tells you there's no treasure, then of course you should stay away. All right, so the clairvoyant in this case is worth 1,000 euros or dollars. But then you can say, okay, there aren't that many clairvoyants around. So this is just an upper bound on any kind of information gathering you can have. So instead, let's go for the detector. But the detector will not give you perfect information. This will be imperfect. So then you have to have some more notation that you could have some false positive or false negative here. And then you need conditional expectations. So now we need to introduce some Bayesian model where we say that, okay, we have a prior model, and then we collect data, and this is defined by a likelihood model, and then we want to use Bayes' rule to get the posterior distribution. And this is done for the data gathering. And then there's some formulas for this, just Bayes formula. And we see that the posterior probability, if you have a positive detection on the detector, is 16%. So it's increased from 1% to 16%, but it's still relatively low. Then if you have a negative measurement with y is equal to 0 at the bottom here, then you reduce your success probability quite a lot to 0.0005. So that means there's information here, but it's not 0, 1 because of the detector uncertainty. So here you can also draw a tree where first on the left here you have the measurement with the detector, positive or negative, and based on this you make informed decisions, and these decisions are based on conditional expectations. So for each branch here you can compute an expected value, and then you see these numbers in dollars. They are the values that each brand is worth. So the conclusion from this sort of example is that the detector data is worth $460, whereas the clairvoyant was worth 1,000. So it's even though there was a pretty good accuracy of 95% on this detector, you lost quite a lot of value. But it's still quite informative. So then in decision analysis, you can say, okay, this is worth 460. So then the pirate should go there and buy or rent this detector if this is cheaper than 460. If it's more expensive than 460, he's better off making the decision right now. So of course, these things are good to illustrate actions or decisions and information gathering options. And in most cases where this value information concept is used, you try to relate it to monetary units. So that means you can actually compare the value information, the VOI, with a price, and then see, okay, is the value information so high that this is worth it? But it's as commonly used to compare sort of different data designs. Should I now collect this kind of data or that kind of data? Or should I maybe go for a certain design A or a design B in space or time? So when or where is the value of information large? Or for what type of data is the value of information large? And if you can't relate it to money, it's also often called value information. So say you want to reduce entropy or reduce variance or reduce prediction error. So then data can help you do this. But of course, what kind of data will help you the most? That's the challenge. So this is used quite a bit in spatial design. So this is a motivation from forestry or conservation biology, where they go in the field and measure say fungi to conserve a forest, or how much timber there is in a forest. So then you can look here at two different designs. One has just random measurement locations scattered all over the field, whereas another design has these two lines that go vertical and horizontal on the domain. And of course the two lines would be much cheaper to do in practice, but maybe not that informative. So at the bottom here you see an equation from Gaussian distributions, and I will use this a bit later. So if you have a Gaussian distribution for your distinction of interest, and then you collect data, and you also assume that the data are related according to a Gaussian relation, linear relation, then your posterior will be a Gaussian with this mean and variance. That's what I'm trying to denote here at the bottom. So in spatial statistics, this is often called kriging, after a guy called Kriege. So then you can relate this to the kriging prediction and kriging variance. And in this simple example, it could look something like this, where you have the prediction to the left, and you have the prediction uncertainty or the prediction variance to the right. And clearly you can see the design. You can recognize the design in these plots to the right. Okay, so now you might see that, okay, we can compute quantitatively the value of information in various ways. And then we can step up and try to do this in space. And then we get to AUV sampling. So now we have an AUV like this. And the challenge is then, okay, this is an autonomous thing, which is really nice. So this can move in the ocean, in space and time. But then you might also have a process there, which evolves in space and time, say chlorophyll changing, or salinity and temperature near a river, or some mine tailings you put in the ocean. All these things changed in space and time. So then how can we best use the resources on an AUV, which are limited because you have some time you operate and you have only funding to do this much, to send the AUV to informative places? That's what we're trying to do here. So where and when, and maybe what kind of data should the AUV collect at this time? So here I will go through examples of all of these three, one on more chlorophyll sampling, and one on salinity temperature in a river plume, and then some mine tailings concentration. So here's one example off the coast of Norway. So actually all my examples are from Norway. It's a bit boring in that way. But this is from an island that has a rich and diverse biology culture. So it's actually a kind of a biological station on this island, which is quite remote in Norway. And here you can see to the right a satellite image where you see patchy sort of plankton in the image. And to the left you can see the island, and you can also see places where AUV surveys were done, and some places where ship-based information gathering took place. So this was then studied with a light AUV that moves like this in the ocean, but this is something we can see just down here too, not the same AUV, but similar. And then we try to guide this in a smart way. So what was actually done here was using two modes. In the first mode, you were just going in a yo-yo pattern in a sort of a long box, bounding box. And then you updated your Gaussian model. So this is a Gaussian process model. So this is in space only. So we're trying to do this relatively quickly, so there's no time variation in the model, even though, of course, there are some time variations in real life. And after this first mode, we switched into an adaptive mode where you try to minimize the variance and also in some hotspots that you aim for. So you look for chlorophyll in this case. And you see when it switched to mode 2 here on the latter parts of time, so to the right in that display, it's more adaptive in the way it's exploring the three-dimensional domain. And then we got some final results. So here you see like a 3D visualization of the prediction, where you see actually some places with high chlorophyll A. And you see the paths that the AUV took in this domain that were adaptively chosen by the AUV at waypoints in the domain. I'll get back to another description of this, which is similar later. And then from the measurements on the AUV, which are shown in red to the right, we compare them with some ship-based measurements of chlorophyll. And then we see quite some variation, and We think that this is location driven. It was not exactly at the same place or at the same time. So there's quite a lot of spatial temporal variation. But now that you have plankton, phytoplankton, and you have chlorophyll A, you can also try to relate this to something that's of biological interest. So on board here there was a silcam that took pictures of species and looked at the species distribution of different sizes. So then I'm not going to go into this much because it's not a field I know very well, and also I'm using this just to demonstrate that, okay, now you can also have a silcam sensor on this. So this is another source of information, but you might not want to use this all the time or everywhere. So then you can check, okay, now a silcam would be really helpful. Let's turn it on, or let's use this now. It's because we think it would be valuable. Our calculations indicate that it will be valuable. Okay, so this was one example, and then I'll get to another example where we tried to map a river plume, and this is something we're continuing now in a project. So here is Trondheim facing north, and I must admit it's not as warm as here in Trondheim these days, but we have some nice sunsets, as you see, in summer. So all places have their beauties. So in this river, especially in spring, there's lots of cold water coming in because the snow melts. So to characterize the plume here, we are looking at separating cold fresh water from saline fjord waters. And then how can we do this with an AUV? So here we thought that, okay, we're looking at a criteria of this cold fresh water mapping. So then we used something that's called an excursion set in statistics. And here's a definition of an excursion set. I'm not going to go into too much math, but it indicates locations where temperature is below some threshold and salinity is below some threshold. So this is a bivariate excursion set. And so this would be random because the temperature is random and the salinity is random, so then also the excursion set would be random. But if the temperature is low and the salinity is low, you would then have an indicator being 1. If temperature and salinity do not satisfy this threshold equation, it would be 0. So this is an indicator variable in space. So here's an example just to illustrate. In the top, you see salinity and temperature, and then you see these indicator variables that are excursions. So to the left here, you have excursions in temperature only, and in the middle below, you have excursions for salinity only, and then to the right, you have excursions in both salinity and temperature. So both temperature is low and salinity is low. So that means, okay, this is the plume we're looking for. At least that's one way of sort of characterizing the plume. Yeah, but so now in order to do this machinery on the AUV, we need a statistical model for temperature and salinity. And then we use a Gaussian process like we did in the other example. And of course, this Gaussian process is not an ideal representation of salinity and temperature variations in a river plume. But it's really convenient because you can easily update a Gaussian process model if you get data. So that's one reason for using it. It's easy to update, easy to compute things with a Gaussian distribution, so it can be done on board the AUV. If we had a more complex model on board, it would take much longer time, and maybe we wouldn't have the computer resources to do so. And still, I like Gaussian distributions because they're relatively simple to compute things on. But there's also quite a lot of flexibility you can put into the mean, which I denote here by mu, and the covariance structure, which I denote by sigma. So in particular, for this case, we have a bivariate Gaussian for temperature and salinity at each location. And this can be trained from ocean models or from some satellite data you have, some other sources of data, or maybe some preliminary AUV runs. So then you can train the mean and the covariance, like a prior model. And in addition to the mean and variance at different location, we also have spatial correlation. So this plot is just indicating spatial correlation decay, where correlation decreases as you go further away. So things that are close are more correlated than things that are further away. So the temperature here would be quite similar to the temperature in Zadar or Split, but it is uncorrelated with the temperature in Trondheim, say, because it's so far away. Okay, so then for how the AUV is measuring temperature and salinity. So then we have, again, a design matrix, F, that picks the location where we're measuring. And now we're measuring salinity and temperature at select locations with some noise. So that's this R matrix here, typically a diagonal matrix with measurement uncertainties. Yeah, and here's what we do for the AUV here. We cover a two-dimensional grid at about half a meter depth. And initially we had some challenges here because it was difficult to get the AUV at the right place because it's moving from saline to fresh water. So then the buoyancy is different, or you need different buoyancy. So we have the AUV moving in this waypoint graph at about half a meter. And then you could tell it to run somewhere in a pre-scripted design, or you could also start adapting. So let me just show you some math, because I think it provides some intuition here. We had these excursion sets, and from the excursion sets, we can compute what's called excursion probabilities at each location. So at some locations, say near the river mouth, the excursion probability is probably close to 1. So you know that, okay, this is fresh, cold water, cold fresh water. And if you go far out into the fjord, you have an excursion probability of 0, because you know that, okay, this is likely fjord water, so the river plume didn't reach this far. But somewhere in between, there's more uncertainty, so that means these probabilities are maybe close to a 0.5. And that means that at the bottom here, you see this integrated Bernoulli variance. So that's P1 minus P integrated over the space. So that means we sum P1 minus P at each cell. And altogether, this is providing an uncertainty measure that we want to reduce in our AUV operation. So it would be dominated by the probabilities that are near 0.5. Okay, so let's go on just a bit. So then you have measurements. You measure with AUV. So that means now you have conditional probabilities. And again, you can compute the realized Bernoulli variance given the data. And this would change depending on what you measure. But for design purposes, to figure out where to sample with the AUV, you can take expected values. So for each design, you can now compute, okay, how much am I expected to reduce the Bernoulli variance by going east or west or north or south on this waypoint graph? And then you choose the one that minimizes this expected integrated Bernoulli variance the most. Yeah, so as you might recall, for the Gaussian, there are some closed form solutions. So based on these closed form solutions, we're actually able to calculate these expected integrated Bernoulli variance, which sounds really horrible. But we can calculate those in closed form. And that means we can sort of have this on the AUV and compute it in seconds. So that means you're not stopping to do some very demanding computations. You're able to do this almost in real time. So that's again a reason for using the Gaussian distribution. Yeah, so this is what goes into this is cumulative Gaussian calculations, where you take integrals of this Gaussian density illustrated here. So if you did a stats 1 class, you probably looked up these percentiles in the Gaussian distribution, and there are similar things in the bivariate or trivariate Gaussian distribution. Okay, then if we go on to adaptive sampling, we have a waypoint graph. So now the AUV has a model inside, a Gaussian model, and as it moves along, it's measuring something, and then it's updating its model, and then it's planning, okay, where should I go next, given all the information I have so far? And then it goes to a new direction, and it updates, or it senses, and it updates, and so on. So this would be an adaptive sampling strategy guided by this goal of ours to minimize the expected integrated Bernoulli variance. Yeah, so this is done step by step in a myopic manner. I won't go into this so much. Let me instead illustrate what's happening. So here's what we have in the prior model to the right. So here's excursion probability going from 0 to 1. And you see, in this case, it's just an illustration. So to the right, it's 0. To the left, it's 1. But then there's a lot of uncertainty here in these probabilities. And this is a simulation study. So what we have to the left is the truth. So we're looking for the red boundary here. Blue is, and white indicates where just one of the two or 0 are satisfied. So then we start moving in this adaptive manner. And here the AUV is measuring things all the time, updating, and then figuring out where to go on this map. And this thing up to the far right is a radar that is changing, always looking at the most informative direction on the waypoint graph. Okay, so this was also done in the field in Trondheim. So then we used a light AUV again, measuring salinity and temperature, and we had 2 runs of 30 minutes of AUV runs. And here's what we got. So in both cases, we started at the center node to the south, and then this is fresh water, cold fresh water, and then it moved up. And then in the first run, it went to the north east, and then you see it zigzags a bit along this front of the plume. And in the second run, it actually turned south instead. So I guess it measured something slightly different in its model, and then it chose to go south west along the river plume. So now we're continuing this using more of an ocean model data to build a prior. So here you see some ocean model results from the salinity coming out of the river. So you see some fresh and saline waters in the fjord. And we see here that there's actually, in Trondheim, there's actually not just one plume. You see the water is also going into some canal and then coming out there. And you see our little Alcatraz island that we have in Trondheim in the center of the image. So we have some initial results here where we do 3D exploration of the plume. So this is ongoing work. So at the end, I'm going to present just very briefly an example with mine tailings in a similar setting. So this is a location in Norway where they a mining company is allowed to sort of release mine tailings into the ocean, and this happens at about 30 meters depth. And then, of course, this should be monitored so that it's not too high. So, because if it's too high, it might cause some environmental problems. So this is again an ocean model illustration here, where you see this going in and out with the tide. So here, this variation is pretty big. So instead of having a spatial Gaussian process, we use a diffusion advection model to represent the variability in space and time, and then have an excursion set again, which illustrates, okay, where is the mine tailings above a certain threshold? So if it's over this threshold a lot of times or in many spatial locations, then it's maybe too much here. So this is, unlike this pirate example, we're not here going directly to decisions. So a decision could be to close things down or to release less and so on, but we are only looking at this excursion set because it's not straightforward to go all the way to the decision level. Yeah, so again we use this light AUV, and then you see over time here how the mean and variance of the mine tailings go down over time, and you see in red the path of the AUV. So then over time the AUV explores a bit in the domain, but then it seems to go a bit back and forth. Here at the bottom it goes back and forth in an area of this domain, which seems rather uncertain and which is sort of at the threshold, where the mine tailings level is at the threshold. So it's like a focused sampling at this boundary. And what you see to the right is the realized Bernoulli variance going down, but it's not always going down. So sometimes if you measure something that is a bit unexpected high or low, this can actually go up, but on expectation it goes down. Okay, so I guess I'm trying to advocate some in-situ sampling here using prior models, and then in this sampling you do this adaptively if needed, and try to sample regions of the space or at times when the value of information is high. And this is similar to active learning, where you try to focus your resources on things that are more uncertain or closer to some boundary that you're interested in. And again, so this Gaussian process model is a big simplification, I know that, and it would be fun to look at more nuanced models. But then again, if you want to have adaptive things in near real time, you need some kind of proxy model for reality here. Okay, thanks.
Thank you so much. And I've just found out actually that I think our third speaker is not here. And we also have some time because you finished early. Thank you. So, oh, the third one's going online? Oh, okay. And when will that be happening? Within the next 5 minutes or so? Okay, so I think we have time for questions, and perhaps questions for Andreas as well, since we've got a bit of time.
Thank you. When you have a robot, I mean, robots tend to like to go in straight lines, and they'll cover distances. So I'm wondering, when you did the exploration, it seemed like you always were sort of very short-sighted, very greedy, and did a lot of zigzagging that wasn't maybe actually from a. I can imagine lots of times you really want to get to the edge of the plume and see that, and so best to go straight. So maybe you could comment a little on that, how much harder that gets. I mean,
yeah, that's a good point. So actually, here in simulation studies we tried like clear myopic strategies or naive strategies that just go where the probabilities are close to 0.5 all the time, and they do much more zigzagging, so they get stuck a lot more than this does. And I think the reason this is better in that sense is that it does compute an expected value over all the data, and it has some element of spatial integration. We are integrating a spatial domain. So it's going still myopic and zigzag, but less so than the naive approaches. But then again, I would like, so we're working on trying more sophisticated algorithms where you go further, or you branch out a tree or something like this to be smarter and look ahead a bit. So we're trying, but again, then you get into some computational challenges. So, but I think that's a very relevant point.
Another question?
Thank you. Many questions, but maybe a related question to this, and we can discuss later. Are you considering, when maximizing your value of information, whether with grid information gain or minimizing the variance, the total flight time, the total energy that you can cover as a constraint to the optimization problem?
Yeah, in a related study on this mine tailings example, we did that. So we put in a constraint on the time the AUV took to go there. So then it was different lines that you could do, and some were more expensive than others. Yeah, I would like to do more of that, because then it also ties in with costs, and you could maybe say that, okay, especially if you have battery challenges or energy challenges, it's tied to IoT systems. How much do you want to use now, or should you save it for later, and so on. But in what I showed here, we didn't use that at all. We set our operation to 30 minutes using this myopic strategy. But it should be better, yeah.
Okay, I sort of have two questions. So, I mean, with regular Gaussian processes, you're kind of, like, they don't really scale well, as far as I understand. Have you encountered any issues with, like, trying to regress, like, ever-increasing data? And then the second one is, have you thought about incorporating localization uncertainty? I mean, because that's kind of linked to what you're observing as well.
Yeah, for the first one, the Gaussian process can be made to scale. There are a lot of tricks that makes it scale reasonably well. So, for instance, you can look at sparse matrices, or you can look at some computational tricks using the data space to do matrix factorization rather than the real space. So these are things we're looking into, but I see that, of course, you can't go to an extreme size. Maybe then at least you would need to do some localization in that calculation as well. But when you were talking about localization, I guess it's where you are. Is it? Yeah. So that's when in some of these operations it was fully autonomous for a long time. In other operations, we pop to the surface every now and then to see where we are, and then we go to the nearest waypoint. But of course, we have already sampled quite a bit then, so we're not correcting for that. We're doing so in hindsight to actually know where the measurements were measured, but not in the real-time operation. So there's no yeah. So in that mine tailings examples, we're basically running a spatial Kalman filter, but it's a spatial Kalman filter in the sense that these mine tailings concentrations are updated like a Kalman filter when you get more measurements. It's not a Kalman filter on the position. The position is assumed to be known. So that's definitely a simplification. We assume we're measuring here, but perhaps we're here. So then if the uncertainty grows too much, maybe you should try to weight this on different places, yeah, or some other way.
Questions?
Thank you for the talk. I was wondering, maybe I missed that part, but how do you initialize all the Gaussian process and the meta model? Because I think it also influences how the robot will start the exploration.
Yeah, ideally from ocean models outputs. So someone has been running heavy computational Navier-Stokes solvers. So in this case, we were using parts of Synmod, which is a Syntef product in Trondheim. So they build ocean models. And then, of course, they are very skilled, but perhaps they're a bit biased. So we adjust them a bit with a simple regression model based on initial runs. Yeah, but we're not having a feedback there. So this ocean model is only given to us, and we're not updating this model. We're using that to train a Gaussian process model. Yeah, but these guys who are developing these models are also interested in AUV data, because they can can use them to sort of refine their ocean models. But that they do that afterwards, not in operation.
More questions?
Thank you. So as you showed in the Trondheim River, so the boundary is not smooth. So you have all these local vortices and changes. How do you cope with that? Can you, for example, get stuck in a local minimum and get back instead of proceeding forward?
So this was related to the earlier question. Yeah, so the challenge here is that if you're near a location where you have 50% uncertainty, you tend to sample there a lot unless you have some kind of heuristic favoring more exploration. But then again, we are integrating over the entire domain. So if there are other places that also have 50-50, we tend to go more away than just a naive method looking at the nearest point and those probabilities. But yeah, it's a balance of focusing your energy, sort of exploitation, and spreading out more into an exploration setting.
Okay, thank you very much, and thank you for the questions.